So now let's try to address both of the problems we encountered while applying linear regression to solve classification problem. Here we will introduce the logistic regression and we'll deep dive into the reasons why we use sigmoid function with logistic regression. So before we address these problems, let's have a quick recap of both of these. The first problem was that our output was not bounded. We wanted a binary outcome or at least outcome in the range so that we can convert it into the binary outcome, right? But so far the output has been in infinity range. It can range from minus infinity to plus infinity. And the second issue was that even a single outlier can break our classifier, right? So let's try a piecewise hypothesis function to address these issues. And let's say our hypothesis function is defined like this. So when we have x or x value less than p, then our model outputs 0, and when it is in a range from, let's say, p to q, then our usual hypothesis what we have seen earlier, and if it is more than q, right, then our output would be 1, right? So this has addressed both of the issues, right? Our output is bounded between 0 and 1. The minimum value is 0, maximum value is 1, and seems like the model is also not susceptible to the outliers now, because we have p cut point here and q cut point here. So outlier would always be in this range, like less than p range, or let's say more than q range, right? And in both of these ranges, our output is always constant. If it is less than p, our output is 0. If it is more than q, the output is 1. But still, there are many issues with this approach. The first issue is that our hypothesis function becomes discontinuous at these points. Hence, the cost function becomes non-differentiable, and that creates a problem in the computation. So essentially, we cannot reliably use the gradient descent method to obtain the parameters. But that is the computational issue. The second issue is that we also need to tune these parameters p and q. Right? We need to tune this based on the data points. And the other problem is, although we have addressed the outlier issue, but we are essentially treating all the points which are falling on this range, on these straight lines, right? We are treating all of these points with equal importance. That means we have lost the relative importance of the points which are falling on this range. Ideally, we don't want our model to lose the sense of the outliers completely. All we want is that it just shouldn't get impacted very significantly by the outliers. So this piecewise hypothesis function will not do the job pretty well. So in the attempt to address the issues we have seen so far, we eventually end up with a very similar function to this piecewise function, and this function is called sigmoid function, which is defined here. Now let's see how this sigmoid function has addressed both of the issues. The first issue was that we wanted our output to be in a fixed range, and we can see in this case that the maximum value is 1, right, and minimum value is 0. Hence it is constrained in the range 0 to 1, and in fact, because this is in 0 to 1 range, these values can be interpreted as the standard probability values. The second issue was of the outliers. So now, if so, basically the outliers would be, let's say, in this range. It can be in this range, or let's say towards this range. So if we observe the probability values for, let's say, 4, right, it would be close to 1, for example 0.99. And if we consider, let's say, an extreme value of, let's say, 20 here, right, its probability value would also be close to 1, let's say 0.999, something like this, right? And because the difference in the probability values is very small, this will not contribute to the overall cost function or to the overall cost massively. Hence, this will not deceive the optimization algorithm and we will get a best fit model, right? So with this, let's introduce logistic regression. So our hypothesis with sigmoid function looks like this. So we have essentially passed our this part to the sigmoid function. Here z value equals to theta naught plus theta 1x, right? And this is called logistic regression because this sigmoid function is also called logistic function, hence the name logistic regression. And how do we do the classification? Simply we take a threshold 0.5 or any other calibrated value based on the dataset. We simply predict 1 if it is more than 0.5, or we'll predict 0 if it is less than 0.5. So although we have solved both of our issues with sigmoid function, but there's still a question like what is so special with sigmoid function which other functions don't have. For example, like we have a 10h function, right? This can also solve our both of the issues. Its output is also like bounded between -1 to 1, right? This -1 to 1. And this can also solve our outer wall issue because this also has the almost flat curve towards both of the ends, right? Here. So what is so special about sigmoid? So let's see this in the next slides. The first key advantage of sigmoid function is that it outputs the values between 0 and 1, and hence these values can be interpreted as the standard probability values. That means when we are getting the probability value of from this sigmoid function, essentially we can treat that as the probability of a point belonging to a particular class, right? The second advantage is that it can solve the outlier problem pretty well. We have already seen this in the previous slide. And the third advantage is that its derivative is super easy. We can even write its derivative in the form of sigmoid itself, right? And it's a huge computational advantage. We can simply compute the sigma z once and can subtract it from 1 and can simply multiply it and we'll get the derivative of sigma z, right? And it's a huge computational advantage. So the other advantage is that the easy functional form of the sigmoid helps in easy interpretation of the coefficients. So we can rewrite this functional form into this form, and this is called log odds form because this is log odds. So from here we can even see the significance of the theta values. For example, if I make small change in x, the log odds would change by a certain amount, which would be decided by the theta 1 value, right? So this is a huge advantage in terms of like explaining the coefficients of the business stakeholders. So if this the transition from this form to this form, if it is not clear, I have given it into the next slide. So you can refer it there. So now we have completed the lesson 1 of the logistic regression model series. So in this lesson, we saw a brief recap of linear regression, and we learned like why exactly the linear regression is not suitable for classification problems. We noticed there were two issues. One was that the linear regression gives an unbounded output, and other was it was extremely sensitive to the outliers. Then we saw how Sigmoid function can easily address these issues along with certain extra advantages, like it provides easy coefficient interpretability and its derivative is super easy, which makes it computationally efficient. So in the next lesson, we'll deep dive into the logistic regression and we'll see how to visualize the decision boundary, how to interpret the coefficients, how to derive its cost function, and so on. So thanks a lot for watching this so far. See you in the next lesson.